here and here. Anyone care to guess? If I take the union over 0 to n not included, but I let n become arbitrarily large, what is this set? No, you're fine, but it's an interval. I'll start you out. It starts
0 to 1.
Well, definitely that's part of it, but I can go from 0 to 2. That's bigger than that. 0 to infinity, right? Because there's no end to this. And all it takes is for the point to be in one of these, and it's in the union. So we can prove that this is equal to that. On the other hand, how about this? For a point to be in this intersection. Oh, man. Seriously? Oh, I did do union there. Okay, fine. Yeah. What do you think about this one here? I mean, this is also interesting. I was just thinking about this. Again, we'd like to prove these assertions. We're just speculating at the moment.
Zero to 1.
0 to 1, right. Because it's a funny thing, because the first one already gets you as far as you can go, right? And you go to a half, 0 to a half, 0 to a third, 0 to, right, as you go on, it's always within that first one. So the union is just this, right? How about the intersection?
0.
It's just the, yeah. So it's a set though, right? So we have to write the set containing 0. So this is an example, by the way, of what's called a singleton. Right? Yep.
Why is there an open bracket for the 0, 1 set?
What do you mean?
Or does it include 1?
It does not include 1 because remember 0, 1 over n by definition is x in the reals such that 0 is less than or equal to x is less than 1 over n. Right? So it doesn't contain the 1 because this doesn't contain the 1 over n. And once we get to 2 or 3, it's just worse. Yeah. Not a proof, but okay, so just giving you some sprinkling of examples. My one last big definition for today, for you guys. We'll talk about topology next class. I think that's I think you've got like one homework problem on that for next next Tuesday. So you should have plenty of time to understand the idea after next class. But and we're not studying topology in general. I just want to expose you to the definition. It's a good discussion for us to have because it helps us to understand some ideas about set theory in a little bit broader context. So my last definition for today is the power set. So if S is a set, then the power set of S, which I denote with like this kind of script P for power, this is the power set of S. It is defined to be the set of all subsets of S. So here's two things that are always in the power set of S. Like, my first remark would be the empty set and the set itself are always in the power set of S. Because we always have the empty set is a subset of the set, and any set is a subset of itself. So there's always at least these two things in the power set of S. All right? Whoa. The clock on this lectern is evil. It says 10:22 right now. So, yeah. That's not helpful. That is very much not helpful. So let me show you guys an example of the power set. Right? Let's look at some example. All right, so what example am I on? Again, we're going to circle back to families and prove some harder things about families next time. By the way, typo in the notes, I should correct. And also in mission 4, the same typo is made, unfortunately. In example 3.3.6, I wanted b sub n to equal to minus 1 over n, comma 1 over n. Not minus nn. If it's minus nn, that's not interesting, and also my claim is not true there. We definitely want minus 1 over n to 1 over n. All right? So that's one thing. All right, so what example am I on here? 6, 7, I guess. Example 7. We'll start out real small. Suppose that we're asking what's the power set of the empty set. What's that?
The empty set.
The empty set, you say. That's right. So this is the only time the power set doesn't have two distinct things in it, right? Because in this case, the empty set and the whole set are the same. What if we ask, check this out, what's the power set of the empty set? So we're asking what's the power set of the set containing the empty set?
The set containing the set of the empty set.
Yeah, we have, well, that's right. But we have the empty set is also a subset of this, right? And also the set containing the empty set. Why do it twice when we can do it 3 times? The power set of the power set of the power set of the empty set. So what's the power set of the set which contains the empty set and the set containing the empty set? Now we've got what? As always, the empty set is a subset, but now also the set containing the empty set is a subset. And also the set containing the empty set is a subset. And finally the whole thing, the set containing the empty set and the set containing the empty set, that set. My words start to fail me, all right? But let's look at example 8. Suppose we have 3 things, A, B, C, right? What's the power set of S? This is probably going to be helpful for you guys if you're lost at the moment. So the power set in words contains all possible subsets of this, right? My computer keeps trying to make me redo Windows. It's evil. Remind me later, punk. So, what do we have? We have, we've got the empty set, right? And how about what else do we have here as subsets? We've got set containing A, set containing B. These are the singletons, the set containing just one element. What are other possible subsets of ABC?
Set containing A and B.
We got, yeah, the AB subset,
containing B and C,
B and C, all right,
containing A and C,
A and C,
the set containing A, B, and C.
A, B, and C. Very good. How many do we got here? 1, 2, 3, 4, 5, 6, 7, 8. Not an accident. How many things are here? 3. 2 to the third? 8. How many things were here? 2 things. How many things over here? 4. Right? 2 to the 2. How many things were here? 1 thing. How many things in power set? 2 to the 1, 2 things. How many things are in the empty set? 0 things. How many things in the power set of the empty set? 2 to the 0, 1. Not an accident. So the power set of a set is strictly larger in size than the set. This is actually Cantor's theorem, that the cardinality of the power set is strictly larger than the cardinality of the set. Now we won't define cardinality until much later, but I think we can appreciate that together. Now, in the remaining 2 minutes of class or so, maybe minute, something to show you guys. I had mentioned that that E was irrational, right? And I conjectured that we could use the fact that it doesn't have a repeating decimal somehow to capture the proof of that assertion, right? So I looked a little bit, and I found out that actually there's a proof due to Fourier. Fourier was an important math physicist of the early, probably mathematician more, of the early 19th century, and he actually had a proof along those lines. So if we look at the website, I actually posted it on the website here, guys. Down here, see this 6 proof that E is irrational? This is Fourier's proof. So the idea is simply this. You take Euler's number E and you subtract, this is its power series expansion for E. This defines E as in terms of a power series, right? E to the 1 is E. And if you look at this, if we assume that E is rational, which is to say that E is A over B, that gives me this. And after some expressions, I can prove that X has to be an integer. So I, on the one hand, from these calculations, prove that X is an integer. And then what follows is we give arguments down here. Come on. We give arguments down here that I prove that X has to be positive, one thing. So this business right here proves that X has to be positive. And then we look at some inequalities and things. And I have another argument here that proves that X has to be less than 1. So you put that together, you have X is an integer, which is positive, and between 0 and 1. So what does that mean about X? Is there any integer which is positive between 0 and 1? There's not, right? So that's a contradiction. And so that we get from assuming that E is a rational number, we get this contradiction here. If you look at the nuts and bolts of it, it rests on the geometric series, like I was conjecturing. This is not my proof. This is like Fourier's proof. I found it at Wikipedia. But I think we can take this proof and actually prove other things. I have a suspicion we could also prove pi is irrational if we twist this proof a bit. This is considerably above the level of proofs I'm requiring of you guys in the homework and stuff, but I thought it might be interesting to have something a little bit more difficult. So we might come back and talk about this more some other day. It's there for you to read if you want to look at it. It's on my website. All right. If you can't find it, email me. Anyway, thanks guys. Oh, for the quiz Thursday, what should we have on that quiz?